Hi, everyone. So I've been working on an algorithm that I guess I've personally been calling ParticleMDI. It's not exactly the clearest what that's meant to mean to outsiders, but what it is a cluster analysis algorithm. So cluster analysis is, conceptually a much more intuitive algorithm than maybe some of the other things you've been hearing about the last couple of days, convolutional neural nets and such. So basically, you observe some data, and the objective of cluster analysis is you want to split that data up into groups. So obviously, this is a very simple problem here. You could just look at that and split the data up into groups, but there's generally much more complicated problems. And so there's many ways that you might want to do this. So there's things like k-means, where you want to split the data up into k different groups, and then you iteratively move observations to the clusters that they're closest to. Another approach would involve model-based clustering. So you assume that all the observations or all the groups in the data arise from a different statistical model characterized by different parameters. So here you might assume that these data are two different normally distributed data groups, one with a mean of +3 and one with a mean of -3. So this is all relatively basic stuff in cluster analysis. So where things get a little more complicated is where maybe you have multiple different data sources. So just to be clear here, this is a vast simplification of it just for the sake of illustration. This itself is not a complicated problem, but if you imagine that each of these contexts reflect two different data sets, and each data set may have hundreds or thousands of different features, they're not just two different features. So what's important to get here is that if we consider context 1 in isolation, we may end up clustering the data as I've shown here. But if we consider context 2 in isolation, we get a completely different cluster allocation. So the problem with this kind of standard cluster analysis algorithms, things like k-means, is that they're not really well equipped to handle multiple different data sets. Particularly, so in this case, we could have the data sets could be completely different types. So one could be normally distributed data, and the other could be something like discrete multinomial data. And ideally, what we want to do is take in both contexts simultaneously. So we may end up with a completely different group in this way. So when does this ever appropriate? When would we ever need to actually do this analysis? So we're kind of coming into this era of genomic medicine where high throughput data, such as things like gene expression and DNA methylation, are going to be more routinely measured for large numbers of patients. And we're going to use these data in order to inform their clinical care. So in doing so, it's important to understand how the genetic variation, or the genotypes, is just how people differ at a genetic level, how that translates into the sort of variation that we see from person to person. So things like maybe blood pressure. So we want to understand how that's influenced by your genetic makeup. So if we perform cluster analysis on genetic data, this can help us find genes which tend to behave similarly under certain conditions. And then these genes we may find have a shared function, which can help us understand what these genes do and how they relate to disease progression. Similarly, we can kind of look at the transpose of this problem, where we look at the genetic data recorded on different patients, and then we try to find groups of these patients. So this is typically done in things like analyzing samples of cancer patients, and we can cluster them based on their genetic data into different kind of risk cohorts. So the data gathered can be very different types, but they'll all be kind of given a different size of the same underlying process. So this is just kind of an example of the data we could have. So these are all, so we have like gene expression recorded under different experimental conditions, or gene expression over time, or interactions under different transcription factors or binding partners. So it's important just to notice that these are all different information recorded on the same genes. And they're all different types. So that first one might be a multinomial data set, the second a time series data set. And so we want to be able to capture all these in a single analysis. So this is kind of like a simple hand-wavy way of how cluster analysis is done in general. So in an ideal situation, what we'd want to do is look at every different possible way of clustering the data and then measure how good those allocations are based on the models that the cluster allocations indicate, and then we pick the best one. So ideally, we could do that, but the sheer number of different clustering allocations just prohibits that. So even if we consider a very simple situation where we have 10 observations that we want to split into 2 different groups, there's 500 different ways of doing that, which that's not that many. It's not that difficult to do for a computer. If we go up to 20 observations, we now have over 500,000 different ways where we can split those up into 2 different groups. Still, that's not really a problem for modern computers, but we're trying to cluster genes here, so we're going to have many, many more than 20 observations that we're trying to cluster. So an algorithm there's an algorithm published in 2012 called MDI, which is what I've been working on improving. So MDI stands for multiple data integration. So it's an integrative clustering method. So it's a clustering method which allows us to borrow information from multiple different data sets. They do this through a Gibbs sampling approach. So Gibbs sampling approach that just iterates through 2 different steps. So for a given cluster allocation, so you might just randomly allocate them to clusters to begin with. You update some hyperparameters. So the hyperparameters are just going to be prior weights the prior probability of assigning an observation to a cluster. And they also introduce this phi parameter, which is a measure of how strongly related the data sets that you have are. So then the second step with the Gibbs sampler is conditional on those hyperparameters. We're going to update the cluster allocations. So how they did this was in a one-at-a-time approach. So you would consider the allocations that you currently have for all the observations. You would iterate through them one by one, and you consider for each one what's the probability that this observation should belong to each of the available clusters, and then probabilistically assign it to a cluster. How they tie in this with bringing the 2 data sets together, or bringing the multiple data sets together, is that the probability of moving an observation to a cluster is going to be inflated if it's the same cluster that observation is assigned to in a different data set. So they found that this could uncover more precise cluster structures than non-integrative approaches, so approaches that only looked at data sets independently. But they found that it could exhibit slow mixing properties. So if we go back here, so what we want to be able to do is kind of traverse this space on the x-axis where we're exploring different clustering solutions. But their one-at-a-time approach only allows you, it kind of minimizes the amount of movement that you can do between like exploring different clustering solutions. So you could end up in a situation where you end up in this small peak on the left here. And in that case, the algorithm it looks around and sees that all the clustering allocations in the vicinity are all worse than what it is. So it considers that one is the best. And then it can end up getting stuck there and not finding what the true global optimum is. So ParticleMDI, which is the work that I've been doing, which is an extension of the original MDI algorithm, it also works it uses a Gibbs sampling approach. However, now we update the cluster allocations using a conditional particle filter rather than this one-at-a-time approach that I mentioned. So particle filter methods are kind of, I guess, they're not typically used for cluster analysis, so they're typically used for state space models, but they conform quite naturally to how you would intuitively perform a cluster analysis. So if we consider just a very simple problem, you don't necessarily need to read this right in here, but if we consider a very simple problem where I've uncovered a large selection of music and we want to sort that music into different genres. So the way we're going to do this is on the basis of the songs themselves, and just to talk about this in terms of multiple data sets, we'll also cluster it in terms of the artwork that's associated with that song or album. So because it's a particle filter method, we're going to use multiple particles. So I'm going to use all you as my particles. So I'm going to play a song. I'm going to ask each of you to pick. I'm not actually going to play the song, don't worry. I'm going to get each of you to assign it to a cluster. So we do that. And so you see this first particle is just one of you who's assigned. So this is with 3 data sets rather than, I'm just talking with 2 here. In this first particle, we've assigned all of the 3 data sets, this observation, to a blue cluster. So it agrees that they're all in the same cluster. And then the third particle assigned 1 to one cluster and then 2 to the other cluster. So then we're going to give everyone a score on the basis of how good their cluster allocation is. So this is going to be based on some underlying model. So if we might assume that the data are normally distributed or multinomial data. And then we're going to sort of give each of the people or each of the particles a score on the basis of that. So we see here that this first particle got quite a bit bigger, so it was given a bigger score than the others. The second particle was found to be quite bad, so it's much smaller than the others. Now, in order to bring all these data sets together, because at the minute the data sets have been clustered independently of each other, we're also going to inflate this weight by this hyperparameter phi, so where the data sets agree, or where the allocations agree across data sets. So you see this first particle where they're all blue, so that's saying that all the data sets are being put into the same cluster, or all the observations from each of the data sets are being assigned the same cluster. So we inflate the weight of that. And in particle 3 at the bottom, 2 of them are being assigned to the same cluster, so we inflate that, but not to the same degree. Then we're going to resample the particles. So we decide that particle 1, whose weight is dominating over the rest of them, we end up with more copies of particle 1, and we get rid of this second particle because its score was too low, so we get rid of that. So now we have more copies of particles which are clustering the data more accurately. Then we reset the particles back, or reset the particle weights so that they all are balanced. And then we move on to the next observation. We go back to the start, we do the whole thing again. And we do this, sweeping through the whole data. And then we update the hyperparameters, and then we start it again. So just to show a quick look at an application of this. So we looked at some kidney cancer data on 243 patients. So we want to cluster the patients here instead of the genes. So the data sets we have with 4 Gaussian data sets, so messenger RNA, microRNA, reverse phase protein array, and DNA methylation. And then we have 1 multinomial data set as well, which are somatic copy number alterations. So we want to take all these data sets in and perform one composite analysis which performs cluster analysis on these patients. So this is just kind of a quick look at how you would look at the results of something like this. So you can see, so along the x-axis and along the y-axis are just the observations running in the same order. And so it's just a heat map then. So the darkness of the darkness indicates how frequently those observations are clustered together. And so you see that the SCNA, which is the multinomial data set, that has a much stronger tendency to cluster together than the others. But it's probably a bit difficult to see here because it's quite faint. But along the other 4 data sets, there is quite good agreement of there's one kind of big cluster here in the top right, and then a kind of a bigger one towards this bottom left. So this is only actually just some results I got in the last couple of days, so we haven't actually looked into how these groups relate to patient risk cohorts. So ideally what we'd like to do is look at, so we have survival data for these patients, and what we'd like to do is look at how each of these patients, or how each of these groups reflect different patient risks. And that's me.